In machine learning, there's a lot of different losses, and in particular, forward KL loss is used quite a bit. KL divergence, as it's also called, is used in particular for something called distillation. And I wanted to explain how reverse KL divergence can be used for on-policy distillation from first principles. In distillation, we have two distributions and we want to make the student match the teacher. The question is, which objective should the student minimize? And this is where we can introduce KL divergence. There are two different KL divergences. Simply, given a teacher P and a student Q, we can define the KL divergence in one direction and in the other. Those are both essentially the same formula with P and Q trading places. I'll explain in this video why forward KL divergence has the same gradient as cross-entropy. And I'll also try to explain, once we understand that, why anyone would want to train with reverse KL divergence. To see the difference between the two, let's have a look at where cross-entropy comes from. The goal that we have here is to develop a binary code for words drawn from the distribution of P that would be as short as possible on average. Suppose you read code words off of a binary tree where left branch is 0, right branch is 1. I would refer you to Huffman encodings if you want to learn more about this. But if y were 1, y would be a prefix of z, which is encoded as 1, 0, and decoding breaks. So conceptually, to make the code as short as possible, we would want it to be prefix-free. Think about it this way. You are receiving a stream of bits, and you want to be able to know if your stream of bits represents x, z, or y, or x, y, or z. It arrives as a stream, so without any separators. To be able to make the difference, you need a prefix-free code. It splits only one way. Now, in this example message, what would be the average cost of bits per word that it took to transmit the message? If you look at the number of bits, which is 12, and you divide that by the number of words that were transmitted, 8, it took 1.5 bits per word on average to transmit this message. Now try to remember that number because we'll come back to it later. To make that number as small as possible, we would want rarer words to get longer codes, right? In a sense, the length is how surprised we would be to see that sequence. The idea of entropy or Shannon entropy is to quantify what the smallest possible average of that length, that measure of surprise, would be under any given distribution. Now, what if we had the same 3 words, but the distributions had changed? Now they start arriving from Q, and Y is the most common word. The average cost has now changed. It's still going to be a weighted average of the same lengths, but this time the weights are going to be taken from Q, the new arrival distribution. The average word length is now compared to the best possible average word length, a quarter of a bit too high. Cross-entropy measures if the data comes from Q, but the code was built for P, what's the average message length? Now this is exactly the problem that we have in machine learning, where the data comes from a certain source of which we don't know the distribution, but we have some distribution, some initial distribution that we are training on. And we want the cross-entropy, which is exactly the measure of the average message length if the data comes from Q, but the code was built for P. And so it makes sense that the smallest possible value that cross-entropy can take is when both distributions are the same, and thus cross-entropy is lower bounded by entropy of either distribution. Now, the wrong code left a gap of a quarter of a bit, as we saw. This gap is the KL divergence. In a sense, it's the extra bits you pay per word for using the wrong code. The formula for KL divergence, as we'll see, can be written And thus most people watching this video will have already seen this formula of the KL divergence, but we can also rewrite it in a simpler way. We'll see that later. It's strictly bigger or equal to 0, and it's equal to 0 if and only if both distributions are equal. Now, importantly, this isn't a symmetric formula anymore like we had with cross-entropy. The first argument is the data source, and the second is our model, or the distribution that we want to transport to the first distribution. Now let's wear our machine learning hats and suppose that P here is a teacher and a very confident student Q bets almost everything on X. Then we would have a very high forward KL divergence, but in the other direction, the price would be very modest. The heart of KL divergence is the direction of these two pressures. Suppose we have a target distribution with two modes, and we want to fit a Gaussian distribution, which has 2 degrees of freedom, that we'll call Q. Now, we could possibly fit it by minimizing the KL divergence of P from Q or of Q from P. The KL divergence of P from Q we call the forward KL divergence, and is going to lead to what's called mass covering optimization behavior. Why is that the case? Well, because if you remember the formula of the KL divergence, in this case, the only place that Q plays a role is as a denominator in the log of P divided by Q. The only way to minimize the KL divergence is thus to make the logs as close as possible to 0, and so to make Q as close as possible to P at every point. Now, what happens if we try to minimize the reverse KL divergence? Well, in this case, to minimize KL divergence, Q only has to minimize the factors that multiply the logs in the formula that we just saw of the KL divergence. In other words, it just has to be very concentrated. Now, just for fun, because I wanted to have some 3D animations in this, let's look at the loss surfaces over mu and sigma. We can see that for the forward KL divergence, there's a global minima, whereas reverse KL divergence, there are 2 local minima. In a sense, we could say that forward KL averages over P's world, whereas reverse KL averages over Q's own behavior. And this is where there's an interesting difference between offline and online distillation. Now, getting back into distillation, I think this is a good place to quickly show the proof that forward KL divergence is gradient equivalent to cross-entropy. We now have all the tools to understand it. We can rewrite by simply using the fact that log of A divided by B is log of A minus log of B. We can rewrite the formula for KL divergence as the cross-entropy between P and Q minus the entropy of P. And if we differentiate with respect to theta, the parameters of the model, because P does not depend on theta, P is the teacher, then we see clearly that the gradient for KL, forward KL divergence at least, is equal to the gradient for cross-entropy. Now, as we saw, this situation with forward KL divergence models a situation in which the samples come from the teacher, or at least from fixed data. So we would say that we are off policy. We could, however, imagine a situation where the samples come from the student, and we're actually taking an expectation under the student's own samples. Because the student is graded on what it actually generates, we would say here that this distillation is on policy. Now, notice that this is not the same thing as a cross-entropy gradient, because the sampling distribution itself moves with the parameters of our model. Now, in what case can that be advantageous? Well, suppose that a student is so small and the teacher is so big that we simply cannot expect the student to represent the whole teacher. In that case, forward KL forces confident mass, where the teacher has none, whereas reverse KL guarantees that what the student will know will be right. We might, for that reason, prefer reverse KL. In summary, we've explained why the gradient of forward KL is the same as a cross-entropy gradient, why that's not the case for reverse KL. And we've also seen why we call forward KL mass covering and reverse KL mode seeking. Thanks for watching.